Hello, everybody. This is our last Zoom meeting, and I plan on going over one problem with hypothesis for the population mean, and then I'm going to go over a scientific study and your expectation and assignment on that. So the hypothesis testing for population mean, the document I uploaded in Tuesday's meeting and I didn't get to it. So I want to do one problem off of that document, and then we will do the scientific study, which is on this meeting. You'll see that uploaded there, and then the assignment that's attached to that. So I'm going to go ahead and share my screen, which I have to plug it in. Sorry, forgot that I have to plug this in. Hang on a minute, please. I used to be able to do AirPlay without this cable, but I don't know. I know I mentioned that last time, but so frustrating when they change things. Okay, so let's see. Share my screen. Let's get this back here. Okay, so share my screen and cable, share. Okay, so this is hypothesis testing for a mean. This is the document that was in, like I said, in Tuesday's meeting. I had two documents. One was for proportion and the other document was for mean. This is the one for mean. We're still going to follow the same recipe. So the same thing that we did in the last example with hypothesis testing on proportion. There's a typo here, so this is referring to graph number 3, not number 2. So I meant refers back up to your level of significance graph with the critical region and critical value. Okay, so we're going to go through this problem, and we're just going to do this first one. Okay, so this one says, ready for college. Let's read the whole problem. The ACT is a college entrance exam. In addition to administering this exam, researchers at ACT gauge high school students' readiness for college level subjects. For example, ACT has determined that a score of 22 on the mathematics portion of the ACT suggests that student is ready for college level math. Okay, some of you may have taken the SAT, which is also another form of these college entrance exams. So ACT is similar to that. To achieve this goal, ACT recommends that students take a core curriculum of math courses in high school. Suppose a random sample of 200 students who completed this core set of courses resulted in a mean ACT math score of 22.6 and a standard deviation of 3.9. Okay, so I would read through this whole problem and then I would go back and pick out the information. So let's continue reading. Do these results suggest that students who complete the core curriculum are ready for college level mathematics, and that is, are they scoring above 22 on the math portion of the ACT? Okay, so let's jump back in here and understand some pieces that might be important. We have a random sample of 200 students who completed the core set of courses, and we know this results in a mean. So that word is really important because we know we are looking at X bar. Okay, a mean math score of 22.6 and a standard deviation of 3.9. So that's S, your sample standard deviation. Okay, so let's just stop there for a minute and go back to how we're going to set up our null and alternative hypothesis. So starting with number 1, and I'm just going to list them out like we did before. So number 1, we need to state the null and the alternative hypothesis. We are testing a mean. We are not testing a proportion. This paragraph has nothing to do with a proportion. We're looking at a mean score. So I know I'm going to use mu. We never use X bar or P hat in the null and alternative hypothesis because we're making a statement about the population. So it's always the parameter, not the statistic. we have equality in the null hypothesis, and then we have to choose whether it's greater than, less than, or not equal to in the alternative. So we have three choices in the alternative. We have either less than, which is a left tail test, or we have greater than, which is a right tail test, or the other choice is not equal, which is a two tail test. Okay, so those are our choices for the alternatives. I got to go back to the paragraph and decide what's helpful here. So do these results suggest that students who complete the core curriculum are ready for college level mathematics? That is, are they scoring above 22 on the math portion of the ACT? So above 22. So is it equal to 22 or is it more than 22? We're testing the hypothesis. So we're going to find evidence to either reject the null hypothesis, which means we're supporting the alternative. So if you reject the null, we support the alternative. If we fail to reject the null, then we do not support the alternative. Okay, so there's number one. We set up the null and alternative hypothesis. Okay, the second recipe is number two. Okay, so number two says verify the requirements. Can we assume the normal model? So number two, for mean, okay, so for proportion, we had to look at sample size less than or equal to 5% of the population size. And we also had to do n times p times 1 minus p is greater than or equal to 10. That was for proportion. For mean, we need to make sure that n is greater than or equal, or let's see, let me start over with that. We need to know, is the population normally distributed? So does it say ACT scores come from a population that's normally distributed? There's nothing in the paragraph that states that. So then we have to ask, so if we don't know, so we don't know about that, it's unknown. Let's say unknown. So then we have to check the sample size. Is n greater than 30? So I come back up to my paragraph, a random sample of 200 students. So n is 200. So yes, oh no, I did two S's, one S on yes. Yes, yes, 200 is greater than 30. So our normal model is, the requirement for the normal model is satisfied. So we didn't know the population distribution. So then the next question is the sample size big enough so we can assume normality? Yes, it is. So now we move on. Okay, so the next one is number three. Number three is where we have to look at the level of significance and then draw a graph with the critical region based off of that level of significance and find the critical value. In my paragraph, there's nothing that says test at the 1% level of significance, test at the 2% level of significance. There's nothing in there that states that. So we get to choose. The level of significance, which is alpha, is not given. So we choose. Remember that a type 1 error, well, let me rewrite that. The probability of a type 1 error is alpha. So the type 1 error is when we reject H naught, but H naught is true. So we reject the null hypothesis, but actually the null hypothesis is true. That's an error. We made an error, and that's the type 1 error. This is back in 10.1, so you learned that already. So type 1 error. So this is related to what we should choose for alpha. If making a type 1 error gives a severe consequence, then we want the probability of making that type 1 error really small. So if people were going to die, or if it was going to harm the environment, or if it was going to be, cost so much money, like those are things that might be significant, you would want alpha to be very small. So alpha might be 1%. If the type 1 error by rejecting the null hypothesis, but the null hypothesis is true, if the consequence of making that error is not detrimental, then we can choose alpha a little bit higher. So think about what that means. If we go back to the null and alternative hypothesis, so here it is. If we reject that the mean is 22 and say that we're supporting that it's more than 22, but if that's an error, so if we reject the mean is 22 and it actually is 22, it's not more than 22, is that going to cause a lot of issues? I mean, certainly it can cause issues, because that could affect like what the score needs to be in order for you to get into a college, or could affect your financial aid. So there definitely could be some consequences of making the type 1 error, but it's not a huge consequence. So I'm going to choose alpha to be 5% or 0.05. So we're choosing that based off of what we're thinking about the severity of the type 1 error, because alpha level was not given, the significance level was not given. Okay, so our task on this part is to draw our critical region and identify the critical value. This is a right tail test because we had greater than. So I'm going to shade all the area to the right. That area is my alpha level of 0.05. Okay, so if I shade the area to the right, then I know that's my alpha level, that's my critical region, that area. I need to identify the critical value. So 0 is always in the middle, whether you're looking at for proportion, because you're looking at a z critical value. This is mean, we're looking at a t critical value. So with the t critical value, you can use inverse t on your calculator. Or you can use StatCrunch. Okay, so inverse t, we need degrees of freedom. Degrees of freedom are n minus 1. So 200 minus 1, or 199. Let me calculate out here. So this is just to find the critical value, and you can use the critical value table. I know StatCrunch, or I'm sorry, I know that my stat lab, in some of the problems they give you that table. You have to make sure you're reading the table correctly, because sometimes the table is showing that it's the area to the right and not to, I'm sorry, area to the left. Gosh, I'm getting my words mixed up. So in the table, sometimes the tables that are given to you in your math problem in the site of my stat lab, sometimes the tables give you the area to the left. So you have to think about what you need, because you actually need the area to the right. So you have to adjust that, maybe by subtracting from 1 or looking at it differently. So make sure that you're paying attention to that if you're using the table. If you're using a calculator, and a lot of your calculators might have a different menu in what to put in here. My calculator, I have to put the area to the right. So 0.95 would be the area to the right. So the calculator wants me to enter it that way. Some of you have an option in there to say whether it's left tail or right tail. And then the degrees of freedom are 199. So when we get that, we end up with, oh, I did wrong. Did I right? Hang on, let's see for a second. It's T. Oh yeah, that's right. I'm looking at something different. Okay, so it's approximately 1.653. Well, I'm going to go out 2 more decimal places. Oh, that's fine. I'll go 1.653. That's fine. So that, remember, that's the location on the number line. So when you find the critical value, that actually is on the number line, the location where you identify the critical value, and then the area to the right of that is your 5%, your critical region, your alpha level. So if you are finding that you, in your homework, that you are off a little bit on these critical values, it might be because you're not using inverse T and you're trying to find a Z critical value. So be very particular, very cautious about what you're choosing for critical value. With mean, you're going to have a T critical value. Okay, so we identify the critical value, we shade the critical region, and now we can finally move on to the next problem. The next problem, or the next part of the recipe, appropriate descriptive statistics. So sometimes when you're looking at p hat, we had to calculate x over n. We're not looking at proportion in this problem, so that's not relevant here. Sometimes if you're given raw data, you have to calculate the mean and you have to calculate the standard deviation. We don't have to calculate anything here because we're given the mean and the standard deviation. So for number 4, we're given the X bar is 22. Okay, I'll go back up here again. X bar was 22.6 and S is 3.9. So 22.6, S is 3.9, N is 200. So those are the descriptive statistics that are given in the problem. We didn't have to calculate anything. All right, now for number 5, it says to find the test statistic with the formula included. Okay, so for mean, we have T equals, not Z, X bar minus the mean, S over square root of N. So that is your critical value formula. So for us, it would be 22.6 is the sample mean. Mu is the population mean, what in the hypothesis. So what you're assuming. We're assuming that the ACT scores are 22. S is 3.9, and we divide that by the square root of 200. Remember in your calculator, if you're going to do this in your calculator, super important parentheses. So your parentheses go around the numerator. Okay, and then you have your division, and then you need 3.9 divided by square root 200. But again, super important, we need parentheses around the denominator. Otherwise, it would just divide by 3.9, and then it would divide again, that whole thing, your result, by square root of 200. So I need to make sure that if I'm in my calculator, I do numerator divided by denominator. Okay, so this is approximately 2.18. So this is your test statistic based off of the data and based off of the null hypothesis. So your test statistic now, we need to mark it on our graph. So number 6 up here. Number 6 says test statistic marked on your graph. And I accidentally wrote 2, but I meant from up here, your critical region. So look at your graph here. There's your critical region graph. Where is the test statistic? It's 2.18. Test statistic is 2.18. So on this number line, 2.18 would be further to the right of 1.653. And then I mark it on there And I know that my p-value is the area from the test statistic or more extreme. So now number 7, we did number 6. Number 7 is make our decision based off of the critical value or the critical region. And then we'll also make our decision based off the p-value. Okay, so number 7, our test statistic right here, 2.18, falls inside the critical region. So it's inside that shaded red area, that 5% alpha level critical region. It's inside of there, 2.18. So therefore, we reject the null hypothesis. So number 7, since the test statistic 2.18 falls inside the critical region, we reject H naught. Okay, number 8, base it off the p-value. So the p-value is on your graph, your test statistic is 2.18. Your area to the right of that is your p-value. That right there is your p-value area. So the area is the p-value from your test statistic more extreme. Because this is a t distribution, not z, then we know that we need to use TCDF. So we're looking at, I can write this out also. We're looking at the probability that t is greater than 2.18. That's really what we're trying to find, that area. On the calculator, we would use TCDF. And then we would put in the lower bound, so 2.18 up to infinity. And we use 1e99 for infinity. And then the degrees of freedom. So my p-value is approximately 0.0152. Okay, you can do that on StatCrunch. You go into, like we did yesterday. I think I wrote that down. Let me grab it. So your little guide here, the step-by-step technology guide for StatCrunch. So we go to stat, and then we can go to T statistic. So in StatCrunch, you go to stat, you go to T statistic. It's not the normal one because it's the T distribution. And then we choose one sample. We choose summary because we don't have the raw data. We have this summary. We already have the mean, the sample mean, and the sample standard deviation calculated. Okay. And I showed you how to do all that yesterday. So I'm not going to take time doing that because I showed you not yesterday, but Tuesday. And then I need to spend time with the scientific study. So investigate that. If you still have questions on that, then let me know right away. So that's how you find your p-value. And then we need to make our decision. So we say, since the p-value, which is 0.0152, is smaller than our alpha level of 0.05, and I'm going to put zeros in front of the decimal just to make it more clear. That's often why we put a 0 in front of a decimal place, because it just makes the decimal more obvious and seen. Okay, so my p-value 0.0152 is smaller than the alpha level. We reject H naught. So let's interpret the p-value. So to interpret the p-value, which is approximately 0.0152. Let me see that here. So I'm going to round this to approximately 0.02, which is like 2 out of 100. So say if we sample size n equals 200, we would find 2 out of 100 with ACT scores more than 22. Okay, so let's now write our sentence talking about the rejection of the null hypothesis. So we say there is sufficient evidence to conclude that students who complete core curriculum are scoring above 22 on the math portion of the ACT. Okay, remember, if we have our null hypothesis, the mean is 22, and the alternative is the mean is greater than 22. So since we had evidence to reject the null hypothesis, that means we support, not accept, we just accept is a whole different, it takes on a whole different meaning, and we don't use the word accept, we use the word support. So support the alternative. So we write our statement involving the relation to the actual problem, involving what it means to reject the null hypothesis and support the alternative. Okay, so that was hypothesis testing on population mean. Same recipe, right? We did this same recipe on Tuesday. We did the same recipe on Tuesday, but we did it for proportions. Really have to, when you're reading your problem, decide what what information is given. Are you given information about a proportion? Are you given information about a mean? Make those decisions first, because your tools are different. Your requirement check is different for proportion than it is for the mean. Your requirement check or your test statistic is different for proportion than it is for the mean. So all of that makes a big difference. Those are the tools that you use. So yeah, we have this fast technology, but if you don't know what you're grabbing and what you're using and what quickly computing for you, then it's useless. You have to understand the problem and know which tools to use to answer the problem. All right, so enough of that. Let's now talk about, I'm going to stop sharing this screen for a minute. And I want to go into different share. So hang on, let me get into another spot. Oh, move me out of the way. I'm going to share my computer screen, not my iPad, because I want to talk about the scientific study and your expectations with that. So scientific study, you need to know right now that this Zoom assignment is worth 25 points. Normal Zoom assignments are worth 5. This one is worth 25 points because it's going to take you a lot more time and effort. So when I go into our classroom under modules and I come into my Zoom meeting and I click on the scientific study folder, Okay, so I'm giving you some tools of what you need to do for the scientific study. So we're going to go over this first document, which is a scientific study. And then there's a link. And there's also like a Word document that you can also look for a scientific study. You're going to research a scientific study. I'm going to open this up. Oh, I hope this is going to show. Sometimes it doesn't show when I open up separate windows, but hopefully it will. Okay, so your task here is you're gonna read the document that, like those first documents that I have given you in the Zoom meeting, so that you can locate your scientific study. Do not pay for a study. The librarians can help you. They're used to me doing this. I do this every single quarter, so they're used to getting these questions, finding a study. Do not find a study that's 45 pages long, because you need to read the study. You want to find a study that you're interested in. So any topic you're interested in, but just make sure that you have the time to read through it and analyze it. So find something that's not too long, but definitely something that you're interested in. You are going to write a paper, basically. It's 4 paragraphs, about 2 pages. Each paragraph has a topic. So the first paragraph, you're going to give a general summary of the study. You're going to, on the second paragraph, talk about the type of experiment or study, the type of data, the sampling method. A third paragraph, you're going to give specific statistics in the study, describe all of those, explaining, interpreting in detail. The fourth paragraph, you're going to talk about any questions or comments and ideas that you still have about the study. Maybe you're wondering why they didn't investigate something in a different way, or maybe you're wondering how it connects to a different topic. So all of these are what you're going to write about in your assignment. You need to make sure you include the source for your study in the MLA format. If you don't know what MLA format is, Google it. It's super easy to find. You all are experts on Google, so pretty confident you can handle that. Okay, so now I'm going to go back to my iPad and we're going to talk about the study that I have provided you. Okay, let's get back in here. Okay, so this is one. Oh, not that one. Okay. Okay, we talked about what you need to do there. Okay, this is a study that I've had for a really long time. And it actually, if you look down at the bottom of this page, let's see, where is it? Right here. This is under, so I'm looking at the page on the bottom of the first page is where I would be. So JAMA is the Journal of American Medical Association. So it's a very respectable journal. It's from September 1992. Okay, so this study is a little bit old, but it certainly has a lot of things in here that we have discussed in our introductory stats class. So that's why I chose it as an example. Okay, so this is about the critical appraisal of 98.6 degrees Fahrenheit, the upper limit of the normal body temperature, and other legacies of Karl Reinhold August Wunderlich. In a scientific study, you usually have this first summary area. So it's like a first paragraph that just pretty much sums up what the study is, what they did, and what the results are, very quickly, very precisely. So the objective is to evaluate critically Karl Wunderlich's axioms on clinical thermometry, the design, descriptive analysis of basal oral temperature data from volunteers participating in the Shigella vaccine trials conducted in the University of Maryland Center for Vaccine Development in Baltimore. The setting, inpatient clinical research unit. The participants, 148 healthy men and women aged 18 through 40 years. The main measurements was an oral temperatures were measured 1 to 4 times daily for 3 consecutive days using an electronic digital thermometer. The results, our findings conflicted with Wunderlich's in that, and just so you know, through the study, I'm just going to be talking about the Fahrenheit degree versus the Celsius. They list both of them, but I'm just going to speak the Fahrenheit one. So our findings conflicted with Wunderlich's in that 98.2 degrees Fahrenheit rather than 98.6 degrees Fahrenheit was the mean oral temperature of our subjects 99.9 degrees Fahrenheit, rather than 100.4 degrees Fahrenheit, was the upper limit of the normal temperature range. Maximum temperatures, like mean temperatures, varied with the time of day, and men and women exhibited comparable thermal variability. Our data corroborated Wunderlich's in that the mean temperature varied diurnally with a 6 a.m. nadir and a 4 to 6 p.m. zenith, and a mean amplitude of variability of 0.9 degrees Fahrenheit. Women had slightly higher normal temperatures than men, and there was a trend toward higher temperatures among Black than among white subjects. The conclusion, 37 degrees centigrade or 98.6 degrees Fahrenheit should be abandoned as a concept relevant to clinical thermometry. 98.9 degrees Fahrenheit in the early morning and 99.9 degrees Fahrenheit overall should be regarded as the upper limits of the normal temperature in range in healthy adults aged 40 years or younger, and several of Wunderlich's other cherished dictums should be revised. Okay, so that right there is the study. It's the summary of the study, and that would be something similar to what you would want to write in your first paragraph. This is very detailed, so maybe not as much detail, but just kind of summarizing the whole study in one paragraph. That would be what you're going to write for your study in your paragraph. Okay, let's dive in deeper now. Okay, this is the second page. The origin of the concept equating 98.6 degrees Fahrenheit with the normal temperature of humans is somewhat obscure, but is generally credited to two different groups of the 19th century investigators. Of these, Wunderlich has been by far the most influential, owing his 1868 magnum opus. And if you speak German, I do have a German last name, but that's the only German word I can say, then you know what his magnum opus is, in which he reportedly analyzed over 1 million auxiliary temperature readings from some 25,000 patients. That is a lot of data, right? A lot of data. In his book, Wunderlich identified 98.6 degrees Fahrenheit as the mean temperature of healthy adults. Okay, so those are important words we're picking out that we know. You are not going to understand everything in your study. You're going to understand bits and pieces of your study with the knowledge that you've gained from the introductory stats class. There's so much more to stats, and I wish that we could be together for a whole year because we could really dive in deeply. But I only get you for 1 quarter, and it's just an introductory stat. So know that what you're reading in your study, you're not going to understand all of it, just some of it. Okay, let's go a little bit further. He also pointed out that the range around 37 degrees Celsius extends from 36.2 degrees Celsius, or I'll use the Fahrenheit, 97.2 degrees Fahrenheit to 99.5 degrees. So there's another word that we know, range. Okay, so I'm not going to read this whole thing to you. I'm just going to pick pieces out of it. Okay, so now let's go to the next page. And in the next page, I need to grab just one more sheet so I can see the places I've highlighted. Okay, so I want to look at this graph here. So in this graph, figure 1, so it says frequency distribution of 700 baseline oral temperatures obtained during 2 consecutive days of observations in 148 healthy young male and female volunteers. Arrow indicates the location of 98.6 degrees Fahrenheit. Okay, so the arrow up here. Okay, so this is a bar graph, right? Is it a bar graph or is it a histogram? There's a question for you. So we first of all know that there's 2 samples because you have male and female. So when I ask you about a bar graph versus a histogram, I'm asking you about the kind of data that you have. We have temperature. Temperature is a continuous variable. It's continuous because we can keep measuring temperature on a scale with more detail. So if I can say 96 degrees, 96.1 degrees, 96.12 degrees, 96.125 degrees. So we can continuously measure the temperature. This is a continuous variable. So this is a relative frequency, counting how many, but temperature is a continuous variable. Okay, so across here, so relative frequency gives us, oh, whoops, grabbed the wrong pen. Thanks. Relative frequency on the vertical axis, temperature on the horizontal axis. Okay, so we're actually counting how many fall in the temperature degrees. So the female and male, you can see where they are. You can see the arrow that indicates 98.6 degrees. So in this graph, you can talk about the shape of the distribution. Is it symmetric? Is it skewed to the right? Is it skewed to the left? Those kind of things. You can talk about trends of the graph. So that's the kind of information you would talk about in a paragraph when you're interpreting your graph. Okay, so you're familiar with relative frequency graphs. So now let's look at this next graph. So this graph, figure 2, the mean is the solid squares, the mean oral temperature and the mean temperature ranges according to the time of day. So let's look at this first bar. So the mean is mean temperature is between 97, I would say 97.5 degrees maybe. Okay, because located right here about 97.5 degrees. And then the range is the high of 99 degrees and the low of a little bit less than 97 degrees, it looks like. So it's the range of the data, and then the mean is where the square is. So you can describe that. And this is for 6 a.m. And we know there's 19 people in that group that they measured the mean and the range from. At 8 a.m., there's 144 in that group that they measured the range and the mean from that group. Okay, so the 4 temperatures are shown at each sample time are the 99th percentile. So there's something else that you've learned. 99th percentile, the 95th percentile, the mean, and the 5th percentile. Okay, so they're talking about up here. So these are the 4 temperatures. So this first one is the 99th percentile. The second one is the 95th percentile. So now this one is the 95th percentile. And then we have the mean. And then the last one was mean, and then the 5th percentile. Okay, so you can describe percentiles. This is a really good way to review some of this terminology. Go back into your guided notebook and review this terminology and remember what percentiles are and describe what the percentile is related to this problem. Okay, so this is a graph you could spend some time on and interpret. Okay, let's keep going. I'm not going to read all this to you like I promised, but I'm going to go a little bit further. Okay, so the results, the 700 temperature recordings from the 148 subjects had a range. Okay, so again, there's a word we know. 96 degrees Fahrenheit to 100.8 degrees Fahrenheit, the overall mean. Okay, the overall mean. And it gives you the mean. You see it has a plus minus there. So it's just giving you a little bit error on the mean. So 98.2 plus or minus 0.7. So 98.2 minus 0.7 and 98.2 plus 7. So they're saying the mean is between these two values. And then it's also given the median and the mode. Okay, so those are words that you know and you've learned. Okay, so I'll come in here. The mean temperature varied diurnally with the 6 a.m. nadir and the 4 to 6 p.m. zenith from figure 2. So that's related to this one we just did, this figure we just looked at. The maximum temperature as reflected by the 99th percentile varied from a low 98.9 degrees Fahrenheit at 6 a.m. to a high of 99.9 degrees Fahrenheit at 4 p.m. So it's referring back to this 99th percentile. So this row. And so they were saying a high of 98.9. What they say here. From a low of 98.9 degrees Fahrenheit to a high of 99. Okay, so there's the low. This is the lowest one, 98.9. And then the highest was this 99.9 at 4 p.m. Okay, so it's just describing this graph a little bit more. All right, let's keep going here. Okay, so comparisons of initial temperature recordings obtained on admission to research ward with ones obtained the same hour the day after admission revealed no significant difference in variability. So you are learning hypothesis testing. So this is related to some kind of hypothesis testing. You've learned hypothesis testing on proportion and hypothesis testing on mean. There's other hypothesis testing. This is on variability. So we use something called an F test, which you haven't learned, but you can still see that there's a p-value here. P is greater than 0.12. So it doesn't give exactly what the p-value is, but it says that it's more than 0.12. If there's no significant difference, then that means your p-value is bigger than whatever alpha level that it was tested at. So your alpha level is going to be bigger than, or is going to be smaller than 0.12. Your alpha level would be smaller than 0.12, the p-value, if there was no significant difference. So you can interpret p-values even if it's for a different test. Age did not significantly influence temperature with the age range through 40 years. This is a linear regression model of p equals 0.99. So we haven't learned we've learned linear regression, but we never really did any formal hypothesis testing with it. So women had a slightly higher average oral temperature than men. So it lists those. And then look at here, t-test. So you have done t-test. We just did an example with the t-test, with the hypothesis test on the mean. Your p-value is less than 0.001, and there's your degrees of freedom. So women had a slightly average oral temperature than men. So the t-test was, the p-value is less than 0.001 with the degrees of freedom of 698, but did not exhibit a greater mean diurnal temperature oscillation than men counterparts. I'm going to skip through some of this, and then I'll say these differences approached but did not quite reach statistical significance. Again, t-test, p-value, and degrees of freedom. Not quite reach statistical significance. Coming down here a little bit more, another p-value. Statistical analysis using general linear model as described in the previous section yielded results qualitatively identical to those reported above. Sex, time, and day, p-values less than 0.01. The race, the p-value is 0.05. Age, smoking, and interaction terms, p is greater than 0.26. So more p-values for each of those categories. There was a statistical linear relationship. There was a statistically significant linear relationship. Okay, so if every time we see statistically significant, we know that the p-value is smaller than the alpha level. And what does that mean? That means that we can reject the null hypothesis and support the alternative. So you need to put it in terms of your problem. You can't just say it means we're going to reject the null hypothesis and support the alternative. What does it mean in relation to this problem? What does it mean about these temperatures? What are you rejecting? What are you supporting? Impulse rate. Oops. So relationship between temperature and pulse rate, regression analysis is p-value of is less than 0.001. Okay, that's probably there. Okay, so that's good for that. Our data suggests that 98.6 degrees Fahrenheit has no special significance vis-a-vis the body temperature of healthy adults when such temperature is measured orally using modern thermometers. In our study population, 98.6 degrees Fahrenheit was not the overall mean temperature, the mean temperature of any of the time periods studied, the median temperature, or the single most frequent temperature recorded. Furthermore, it did not fall in within a 99 confidence limits. So there's your confidence interval for our sample mean. Okay, so there's your confidence interval for your sample mean. So we're looking at 98.1 is less than mu, which is less than 98.2. These are degrees Fahrenheit. Wonderlic regards 100.4 degrees Fahrenheit as the upper limit normal body temperature range, and by extrapolation, any temperature greater than 100.4 degrees Fahrenheit as a fever. Modern medical textbooks differ in their definition of the upper limit of normal oral. A little bit more, according to Wonderlic, women have slightly higher normal temperatures than men and often show a greater, more sudden changes of temperature. In a study of 9 healthy young adults, 6 men and 3 women, corroborated both observations. In the present investigation, we were able only to corroborate Wonderlic's former observation. Wonderlic did not personally study the influence of race on body temperature. Instead, he deferred to the observation of Livingstone travels in the South Africa, showing temperatures of natives 2 degrees Fahrenheit greater than his own. In the present investigation, there was a trend towards higher temperatures among Black subjects than among white subjects, with differences approaching statistical significance. There's your t-test, there's your p-value. The general linear model also gave a p-value of 0.05. In view of the data presented and the work of several other investigators, we believe that 98.6 degrees should be abandoned as a concept having any particular significance for the normal body temperature. In the early morning, this should have a Fahrenheit. That's a typo on this paper, but that should be Fahrenheit. Overall, should be regarded as the upper limits of the oral temperature of healthy adults 40 years of age or younger, and several of Wonderlic's other cherished dictums should be revised. Okay, so that is the study. It tells you the study was supported by the U.S. Department of Veterans Affairs and by the U.S. Army contracts. The authors thank these people. Okay, and then you have your references. So they're always including references. You always have to state your source. So when you're writing your paper, you need to state your source and what references you used. You're only going to give me, unless you use some other reference, but you would just give me where this article came from. So in MLA format is what I want. All right, so that is the scientific study I wanted to go over. I want you to have a good experience with this. It's going to take you time to research a study. So make sure that you are not starting on Monday when it's due Monday night. You absolutely need to start today or tomorrow. This write-up is not due until Monday. Contact the librarians if you need extra help. If you're using the internet as far as just like Googling something, that is not a valuable source. You need to get a scientific study from like a journal or something that is very sound with the processes that they use, the scientific processes. That's why we go through that recipe 1 through 8 or 9, whatever it is, because we go through all those steps in a very formal manner that avoids bias, and we end up getting the results that are scientific. All right, if you have questions, please let me know. What I need you to turn in for me today is nothing, because today is not due until Monday. On Monday, you are going to turn in your scientific study, and then you are going to write your 2 reflection questions. Okay, everybody. No more Zoom meetings. Bye.